Welcome to M1. Today we're going to look at Chapter 6, Momentum and Impulse. And this is more of a kind of a recap video. Now, momentum is mass times velocity. And if I look at the unit, say kilograms times meters per second, that's one option for the unit. Just based on what we've got here, mass times velocity. Another one is Newton seconds, and this kind of comes from F equals ma. Newton seconds is what we often tend to use, but it doesn't really matter. They're both kind of interchangeable. Now, the second thing within this unit is impulse, and impulse is force times time. So if we think of momentum is the mass of a body moving at a velocity, and impulse is the force that is applied or acts over a set amount of time. And what you'll notice is that units of impulse are Newton seconds. Force in newtons, time in seconds, Newton seconds, which is why we tend to use this for momentum as well. And using F equals ma and V equals U plus AT, we can rearrange the impulse formula and we can get one that then links in with momentum. So this would be my final momentum minus my initial momentum, or the change in momentum. And this is given a name. It's called the impulse momentum principle. Now, part of this unit is also about the conservation of momentum. Okay, and what that basically means is that any momentum we had before any kind of impact is going to be equal to any momentum we have, or total momentum we have after that impact. So that momentum, the amount of it isn't going to change. Obviously, in terms of the actual bodies that are involved, those velocities and things will change. Okay, but that total amount of momentum will remain the same. Okay, obviously in actual practical real life there is other things going to be lost due to other things that are happening, but in terms of what we're looking at in M1, they will be exactly the same. So what that will look like is that our mass and velocity of one body plus our mass and velocity of the other body before the impact will be the same as the mass and velocity plus the mass and velocity of the other objects after impact. So our momentum before, so two momentums before is going to be equal to the total of our two momentums afterwards. And then in terms of a diagram, and these kind of questions, is often useful to have a diagram. If you think of the velocities before, okay, the velocities may be going and then they collide, and then afterwards we have a new velocity. Okay, so you're kind of assuming here they're just both going in one direction. Obviously with velocities being vectors would mean that if you assumed the wrong direction and it actually went in the other direction, you get a negative velocity. So nothing too difficult there. So this is before and this is afterwards. And then the only other thing to add in is these two impulses. The impulses will be acting as so. And this is just because Newton's third law, so when these bodies collide, it's going to exert an equal and opposite force on each other, which is why the impulses are going to be pointed in the opposite direction to each other. So now we've kind of just recapped and talked about everything within this unit. Let's start with a couple of examples on each thing. So we build up from the momentum and impulse through to the conservation of momentum. Okay, nice straightforward example to get us started. ball of mass 0.5 kilograms is at rest when it's struck by a bat and receives an impulse of 15 Newton seconds. Find the speed immediately after it is struck. So we know the mass is 0.5 kilograms. We know its initial speed u would be 0 meters per second. V is obviously what we want to find. And we also know that I is 15. So using our impulse momentum principle, we can say that I is mv minus mu. So 0.5 v minus 0.5 u, and I is worth 15 Newton seconds. Okay, now our u is 0, isn't it? So this one is 0.5 times 0. So we're left with just 0.5 v is 15, so v must be 30 meters per second. So very straightforward, hopefully nice and easy just getting us started. Now, in this example, we have a ball of mass 0.3 kilograms moving along a horizontal surface, and it hits a fixed vertical wall. So I always like to do a little sketch on a lot of these as we start to get into them. So we've got a ball, it's 0.3 kilograms, and it's going to hit this surface at 3.5 meters per second. Okay, which is obviously given here in the question. The ball rebounds at right angles, which is perfect, exactly what we want. Given that the magnitude of the impulse exerted on the ball by the wall is 1.8 Newton seconds, so we've got our impulse here, and find the speed of v afterwards. It's worth noticing or remembering that the impulse the ball puts on the wall and the wall on the ball are going to be the same. They're the same thing, yeah? Equal and opposite forces. So impulse is my change in momentum. Okay, and direction matters here. So my impulse of 1.8, you can see I've chosen that's going in the same direction as my final velocity. So 0.3 v. Take away, and then we've got 0.3. Now, my initial speed is in the opposite direction. So I need to make sure I show that with a negative sign. Remember, velocity is a vector, so direction matters. So my impulse is going in this direction, v is going in this direction, so I have to look at what u is in this direction as well. So that will give me 1.8 equals 0.3 v plus 1.05. And from here, it's just a matter of simplifying. Give me a velocity of 2.5 meters per second. And this also makes logical sense, doesn't it? Ball hitting the wall and then rebounding off, and that speed or that velocity is just a little bit slower. Now, this example, we've got two particles, A and B, masses 2 kilograms and 5 kilograms. Moving towards each other on the same straight line, so it means they are going to collide, perfectly into each other, not going to just glance or graze or anything like that. So like a full collision, and it's a smooth surface, so there's no friction to worry about. Before the collision, the speeds are 6 and 4 meters per second. Afterwards, A is going in the opposite direction at 1.5 meters per second. So we need to find the speed and direction of B after its collision, and then the magnitude of the impulse given by A to B in the collision. So this one, when we think of this impulse of A to B, it would be the same as B to A, wouldn't it? Equal and opposite forces there, so that impulse will be the same whichever way around we look at it. So if I think before the impact, we've got particles A and B. Okay, and these are 2 kilograms and 5 kilograms. And they're moving towards each other. So I can think of it very much like this one's going this way at 6 meters per second, and B would be going this way at 4 meters per second. Okay, and this is kind of before my impact. Now, afterwards, the direction of A changes. It's reversed, it says here. So the direction, it was going left to right, it's now going, sorry, it was going, left to right, now it's going right to left, and it's 1.5 meters per second. Okay, now with B, we don't know. So with B, I'm going to assume it carries on going in the same direction. I think it makes more sense to assume that. If I think about it logically, it was a heavier object hitting it, it's changed the direction of this, it's most likely going to carry on in the same direction. Obviously, if I get this guess wrong, I'll just end up with a negative value, which will then tell me that it's going in the other direction. So it makes no difference, but I just think, kind of logically, that is what I would expect to happen. Incidentally, I normally do this on one diagram, put the before above and the after below. I'm just doing on 2 separate diagrams here just for a bit of clarity for you guys at home. Now, since we have the mass and velocity of everything before, and we have mass and velocity and mass of everything afterwards, we've only got missing this velocity, we can use the conservation of momentum to help us work this out. So we know that my mass times velocity, so that momentum of each of my bodies before is going to be the same as afterwards. So that means we've got 2 times 6 plus 5 times 4, and that's going to be equal to 2 times 1.5 plus 5 times my V2. Now, what I haven't put in yet is the directions. So if I think about this, I've got my velocities, I do need to pick a direction. So I can go with left to right, the same as what A is, or I can go, well, actually, I'm assuming that 3 of these are going to end up going from right to left. So I can pick my right to left as my positive direction. So you just want one direction as your positive one. So this will mean that the 6 is a negative 6 in this case, and the 4, the 1.5, and the V2 is going to be positive. So now we've got minus 12 plus 20 equals 3 plus 5V2. So minus 12 plus 20 is 8, then take away 3 is 5, so 5 equals 5V2, so V2 is going to be equal to 1 meter per second. I'll just write it up here, 1 meter per second. Okay, and it is the direction as I've shown on here, but it is also worth making this kind of statement. So what I would say is, look, it was already going from right to left, it's still going right to left. So 1 meter per second in same direction as before the collision. Okay, so it's just making it very clear to the examiner that it's not just about the diagram. My diagram is right, but I'm also making a statement here that it hasn't changed its direction. Okay, so essentially that motion of B in terms of its direction of motion is unchanged. Now for part 2, we are talking about the impulse. Now remember, the impulse comes off these at impact at the opposite direction. Okay, and as I said before, it doesn't matter which way round we are thinking of. So if I'm thinking of the impulse of A, okay, so for A, and the impulse is going in that direction, the right to left direction, isn't it? Get rid of those actually. So impulse, and this is change in momentum, isn't it? So we've got 2 times my 1.5 minus 2 times my 6. And again, I just need to be careful with the direction. The direction we're going is from right to left. So my 6 is going to be negative. Okay. Obviously, with these being the same size, often you might see this kind of written a little bit more like v minus u as well, if that mass is the same like it is in this kind of case. So we've got 3 plus 12, so that means that we have a total of 15 there Newton seconds in terms of its impulse. Okay, equally I could have done the impulse of B as well. They're both going to be the exact same answer. Okay, makes more sense to use A as we have it before and after, whereas with B we've only got the value that we worked out. So it's safer to use A because we're using the values within the question rather than a value we've calculated. But just to show you, if I did use B, well, B, I'd be looking in this direction, left to right, because that's where the impulse direction is. So I'd have 5 for my mass times by negative 4. Apologies, because my final one is negative 1, isn't it? Minus 5 times minus 4. Yeah, because both of my velocities are going in the opposite direction to that impulse. The impulse is going left to right. Okay, which is why I choose that as the kind of positive direction here. So we've got here minus, I've added them instead of doing it, minus 5 plus 20, and you can see that is 15 Newton seconds. So it is the same, and it should be the same. That's what we expected. Obviously, it would end up being different if I made a mistake here. But like I said, we use this one because we've had all the values from the question. It makes more sense. Now I'm going to give you a few of these types of questions to try. And as always, I'll put the answers at the end of the video. It's worth pointing out that while I used impulse here, you could also use your Suvat equations So V equals U plus AT to find A, and then F equals MA to find the force. So that is another way you could have worked out part A.